We're now going to do a video about the mole, and there are several videos on amount of substance which separate out all of the different calculations you can do in your first year of your A-levels, and this one will go through the basics using Avogadro's constant and using the mole equation, moles equals mass over AR or MR. So let's start with the simplest things which hopefully you should remember from GCSE, calculating relative molecular mass. Now, relative molecular mass is equal to the relative atomic masses of each element added together. So you just have to add all of those together, which means you'll need a periodic table. So you haven't got one by you, please get one now. Now, we're going to put the elements from the periodic table and the symbols on as we go through these calculations. So the first one is hydrogen. Now, if you want to do the relative molecular mass of hydrogen, you also need to know something else, and that is, in this video, we use something called HF bronoclad. There are other versions of this that help you remember these molecules. Now, all of these molecules in HF bronoclad happen to be diatomic. So that means when they're separate, when they're on their own, when they're not bonded to anything else, and they're on their own, they will always be in a pair, okay? So hydrogen, fluorine, bromine, oxygen, nitrogen, iodine, chlorine, and astatine. You'll almost certainly never come across astatine being used in any major way, but the rest of them are very, very common. So if we look at the relative molecular mass of hydrogen, that means because we know HF bronoclad, we know that hydrogen is in a pair, it's diatomic. Okay, and if that is the case, the molecular mass, which is denoted as MR, is going to be 2 times the atomic mass of hydrogen. So we get our atomic mass from hydrogen here, which is highlighted, which is 1.0. That's our 1.0 there. We've got 2 of them. So therefore, 2 of those is going to be a molecular mass of 2 grams per mole. So the unit for molecular mass, or relative molecular mass, is grams per mole. Let's try another example. Calcium chloride. Now, calcium chloride, made of calcium, we can see our relative atomic mass of 40.1 there, and then we've got chlorine, relative atomic mass of 35.5. So remember, it's all the relative atomic masses added together. We then need to look at the formula, and the formula here says, look, there's 1 calcium because there's no number by the calcium, there's no little number, okay? And then we can see this little 2 by the chlorine, which means that there are 2, or in this case chloride, there are 2 chloride ions and 1 calcium ion. But essentially calcium and chlorine, 1 calcium and 1 chlorine. We then put that into our calculation, and we can see we've used the relative atomic mass of calcium and we've used the relative atomic mass of chlorine. And we've put the 2 in to say there are 2 chlorines, and we have 111.1 grams per mole as the relative molecular mass of calcium chloride. Let's do a slightly more complicated example with brackets. Again, we're going to get the elements off the periodic table. We've got 40.1 for calcium, 14 and 16 for nitrogen and oxygen. Now, this is where people normally come unstuck. It's because they have to notice how many elements are there because of the brackets. Now, essentially, what if you do a bit like maths and you separate out the brackets and you go, right, okay, let's take those out. Now, there's 2 NO3s because there was a 2 there, so I've just taken 2 out. Now, that means that you're leaving behind calcium 2+ ion and 2 nitrate ions. But essentially, if we're doing relative molecular mass, remember electrons don't really have a mass of any significance, and therefore we just ignore that in terms of mass calculations. So that means we know we've got 1 calcium and we've got these 2 nitrates. Now, if we split those 2 nitrates up and say, right, how many nitrogens are in those? Well, there's 2 nitrogens there, and then there are 6 oxygens. And we put that into our calculation. So here you can see I've got my calcium, here I've got my nitrogen, and here I've got my oxygen. And that equals 164.1 grams per mole. Now that we've calculated the relative molecular mass, we can also go on to using the term mole. Now, the mole is basically the relative atomic mass of an element or an ion, or the relative molecular mass of a molecule or a compound in grams. So 1 mole, for example, if you have lithium, lithium has a relative atomic mass of 7, and therefore 1 mole of lithium will be 7 grams in mass. Now that mass of 1 mole is also known as the molar mass. So sometimes in questions you'll see give the molar mass, and it just means the molar mass is just the mass of the number of moles that you have. Okay, so if we then carry on and look at how do we calculate this, we have mole equals mass over atomic mass or molecular mass, depending on what you have. And we'll go through a few examples of that. So carbon, starting off with. If we have 1 mole of carbon can be calculated here. If you look, if I have 12 grams of carbon, let's say I had a sample of 12 grams of carbon, I would divide it by its atomic mass in this case because it's carbon, okay, and get that off the periodic table, which is 12. 12 by 12 equals 1 mole. So if I had 12, that means basically if I had 1 mole of carbon, okay, I would have to use 12 grams. 12 grams would equal 1 mole, okay. Now, if we then looked at it and say, well, what will half a mole be? Okay, well, that's half the mass, essentially. So 6 grams divided by 12, and that's half a mole of carbon. And you use this equation anytime you want to work out moles, or you want to work out molecular mass or mass by rearranging the equation. Now, let's put that up there and then look at some examples. So if we have, what is the amount of hydrogen in 12 grams? Okay, so you have 12 grams. So this time, the amount, which is a really important term, is often used in exam papers and things like that to denote the word mole, okay? So our exam tip right now is to say amount in a question means moles, okay? So if you see it, that's what you need to do. Remember the diatomic elements when determining moles. So we've got HF bronoclad. Okay, and that's really important to you remember. So if you ever come across this, remember it's only when they're on their own. We're talking about hydrogen here, so that means hydrogen is H2. Okay, and if hydrogen is H2, taking it over there, okay, that means we're going to have to include that in our relative molecular mass calculation. So we've got our amount of hydrogen, and we know that it's diatomic, so let's put it into the calculation. So let's just say this time we had 12 grams of the hydrogen, as we said in the question. Our relative molecular mass is not 1 as it says there. Remember there are 2 hydrogens in the molecule, so it's 2 times 1 is 2, and therefore that means if I had 12 grams I would have 6 moles, and that's my amount of hydrogen as in my number of moles of hydrogen. Our next question is going to involve significant figures. So if we look here, what is the amount of calcium nitrate in 19.9 grams? So if you're used to significant figures, there's a few rules that you need to know. First of all, we're asked for the amount, which means we need to calculate the number of moles. Okay, and then if we look at our calculation is moles equals the mass, which is 19.9, divided by our molecular mass, which we calculated in a previous slide, okay? And we've got this number here, very long number, which often comes out on your calculator. But we need to know what to write down on the exam paper. So let's look at our rules. Our exam tip here, significant figures, really, really important, these 2 rules. Always give in the correct number of significant figures as stated by the question. So if the question says to you 3 significant figures, do it. If it says 2, do it. Okay, read the question properly. The second thing is, if it says give it to an appropriate number of significant figures, this is when you need to look at the data in the question, so the data given in the question. This one's quite simple because it only gives one bit of data. It's the data you're using in the question, not necessarily all data in the question. So here, look here, we're given 3 significant figures, 1, 2, 3 significant figures. So that means basically if we then look at this and we look at here, we need to do it to 3 significant figures, and you look, it says 0.121. Okay, then we've got 2. Well, 2 is less than 5, obviously, so therefore 1 will not be rounded up. It will just stay exactly the same. So our answer here is 0.121. Okay, 0.121. And that is to 3 significant figures, but we knew it was 3 significant figures because it's an appropriate number of significant figures is the minimum amount of significant figures used in the question. So we have 3 in this one, dead easy, but imagine you have a question where there is a few different significant figures. Always go for the minimum used in the question, okay? That's really, really important because that can be an extra mark and it's not a mark you want to easily lose. So we're now going to talk about Avogadro's number, sometimes referred to as Avogadro's constant. So it tells us the number of particles in 1 mole. Okay, so 1 mole of a substance has a certain number of particles in it. Now that can be electrons, that can be molecules, that can be atoms, etc. Okay, so that number is 6.02 times 10 to the 23. So it has a very large number with lots and lots of zeros after it, absolute huge number. Okay, so in 1 mole we have that many electrons, or we have that many molecules, or that many atoms. Okay, now if you want to work out the number of atoms that you have specifically for a specific number of moles, all you have to do is take the number of moles that you're given and times it by Avogadro's number. Now Avogadro's number is shortened to Na, okay, which stands for Avogadro's number, okay, and we're going to go through a few examples of how you can do that. So we put Avogadro's number in the top right corner so you can refer to it, and we've got our number of atoms equals mole times Avogadro's number as well. So first of all, a method for when there is a substance made of the same element. And it's 2 types. It's the giant metallic and the giant covalent structures specifically, okay, usually, and the ones that have the same atom throughout, really. Okay, so we have same element, and we've got graphite, graphene, diamond, and Buckminster fullerene, and of course metals. So let's take diamond. Now diamond is just made of carbon. Okay, so it's the same element. Okay, so all we have to do, if we have 0.4 moles of diamond, we take, if we want to know the number of carbon atoms in diamond, we take the number of moles, times it by Avogadro's number, and then we'll get 2.408 times 10 to the 23. Okay, it's as simple as that, just times the number of moles by Avogadro's number, and you'll find out the number of atoms in there. And once you've done that, you can move on to slightly more complicated examples, for example, molecules. So if we look at molecules, we have got oxygen here. So they have more than 1 atom per molecule. Carbon dioxide, for example, oxygen, nitrogen, anything in HF bronoclat, as you can see down here. Okay. Now we know that there are 2 atoms per molecule because it's O2, and it's signified again by the diagram here. 2 atoms of oxygen per oxygen molecule. So what we do is we take the number of moles that we have here, and we want to work out the number of atoms, and we want the atoms of oxygen. Okay, so we want our atoms of oxygen. We've got our number of moles. Okay, and that number of moles, okay, in there, and it doesn't matter what order you do it in really, in the number of moles, if I have 0.4 moles, I will have twice the amount of moles because in 1 molecule I have 2 atoms. So 1 molecule is 2 atoms, that means 1 mole will have 2 moles, that means 0.4 moles will be 0.8 moles, okay, because we have 2 atoms per molecule. We'll take that and then times that by Avogadro's number, okay, times 10 to the 23. Now if that is the case, we'll end up with 4.816 times 10 to the 23, and that will be my atoms of oxygen. Okay, so it's really, really important that you recognize these ratios. The ratios are very, very important. If I have a molecule with, for example, 2 atoms per molecule, that means if I have 1 mole of it, there will be 2 moles of the atoms. If I have carbon dioxide has 3 atoms per molecule, so that would be for every mole of carbon dioxide, I would have 3 moles of all of the other atoms added together. But that is how you do that with oxygen. We'll move on to do it with other examples. Our next example is molecules. So we have the molecule methanol on the board here, and we can see that there's a question, what's the number of atoms of hydrogen in 0.125 moles of methanol? And we can see here from the formula that we have 3 atoms of hydrogen plus the one here, which is 4. So we have 4 atoms. That means per molecule of this methanol, we have 4 atoms of hydrogen. That means if we have 1 mole of methanol, we have 4 moles of hydrogen. It's really important to see that connection. So 1 mole of methanol would be 4 moles of hydrogen. So if we want to know the atoms of hydrogen again, so let's write out our atoms. Okay, so we've got our atoms, and again, we can do it with our 6.02 times 10 to the 23. Okay, and you can do it in a slightly different way. It's all the same maths. Let's try it this time and say, right, okay, how many moles do we have? Well, we have 0.125. We know in 1 mole we have 4 moles of hydrogen, so we can do times by 4. So that means in 0.125 moles of methanol, we'll have 4 times that of hydrogen. We'll then take that, and then we'll times that by 6.02 times 10 to the 23. Okay, so, and that will mean that we end up with 3.01, okay, atoms of hydrogen. Okay, and that's what we end up having. So it's really important you know these ratios. We're now going to go from molecules to ions. So let's have a look at an example. With an ionic compound, you will need the numbers of each ion or polyatomic ion in the compound. So if we take an example, and the example we've got is sodium carbonate, and we want to know the atoms of sodium, okay? So we got 0.4 moles. So if we look here, the sodium's got a 2 by it. So that means for every 1 mole of sodium carbonate, there will be 2 moles of sodium. Okay, so it's really important that you know how to read that. So if you put that into a calculation, if we have every 1 mole of sodium carbonate, there are 2 moles of sodium. So for 0.4, it is going to be 0.4 times 6.023 times 2. Okay, and if that is the case, you put those numbers into the calculator and you'll get 4.816 times 10 to the 23. Let's do a little bit more complicated example. So what are the number of atoms of oxygen in 0.4 moles of aluminium carbonate? Now we're looking at the oxygens here. Now it's important from earlier that you realise that if there's brackets, we need to times everything inside the brackets by the number outside the bracket. So 3 times, in this case, 3. So 3 times 3 for the oxygen is going to be 9. So that means that for every mole of aluminium carbonate, there are 9 moles of oxygen because of this 3 times 3. Okay. So for 0.4 moles, we do our calculation again. We've got Avogadro's constant times by the number of moles, the whole thing times by 9. Remember, you can do this in any order. Okay, and that will equal 2.1672 times 10 to the 24 atoms of oxygen for every 0.4 moles of aluminium carbonate. So what about if we're given the mass? So we've got a question here, calculate the number of atoms of carbon in a pencil lead with a mass of 0.15 grams. So if that is the case, we need to know the number of moles. So we need to use this equation with moles equals mass over AR or MR. In this case, it is carbon, so it's AR. So if we look at the molecular mass of carbon, atomic mass of carbon, we have that as 12 grams per mole. So that would be 0.15 divided by 12, gives you 0.0125 moles of carbon. Now we use our equation again, which is number of atoms equals your number of moles times Avogadro's constant. So we've got a number of moles from up here, and we've got our Avogadro's constant here. So we get 7.525 times 10 to the 21. So a really important process. Number 1, if you're given a mass, find the number of moles. Number 2, times that number of moles by Avogadro's number. You can also complicate that a little bit if you have brackets, and you'll need to use the previous method if you know there are more than 1 mole per mole of substance of a particular element. So we're now going to look at 2 types of questions which people can easily get confused about. Now, the first one is calculating the number of electrons in terms of moles, okay, and then calculating the actual number of electrons. Now, these are often MCQ questions and are worth practicing. So the first type is going to be calculating the number of electrons in terms of moles. So remember, moles is just a number. So moles is just 6.02 times 10 to the 23. Okay, and it would just be the mass of those moles if you're talking a mass of it, or for example, number of moles, which is what we're going to calculate in here. So if you think about it, we can do it in terms of this following question. The number of moles of electrons in 0.5 moles of hydroxide ions. So if you think about it, one hydroxide ion will have a certain number of electrons. And for every one hydroxide ion, you will get an exact number of electrons. So we need to determine what that number of electrons is. So the number of electrons here, you can see if we draw hydroxide, lovely diagram with our hydrogen electron, oxygen electrons, and then the extra electron to create the minus. Okay, we think there's 8. The common mistake is to forget the fact that there's an inner shell that you don't normally draw. And you don't normally draw that, so you forget it. Okay, so there's actually 10. So that means if I have 1 ion, I will have 10 electrons. So if you just extrapolate that upward and say, right, okay, that means if I have 1 mole, which is just 6.02 times 10 to the 23 ions, but if I have 1 mole, I would have 10 times as much moles of electrons. So therefore, 1 mole of this will give 10 moles of electrons. But I haven't got 1 mole, I've got 0.5 moles. So all I have to do is take the 0.5 moles and times it by 10, because I have 10 electrons. So 0.5 times 10 is equal to 5 moles. So if I have 0.5 moles, I will have 5 moles of electrons. That means 5 times 6.02 times 10 to the 23, huge number. Okay, and it's as simple as that. You've got to decide that ratio by counting the number of electrons. Our next question about Avogadro's number and electrons is to calculate the number of electrons in terms of their number or their quantity. So if we look at the number of electrons that are in 0.125 moles sample of calcium, so we've got calcium here. Okay, and we know in calcium that we have 20 electrons. It's a bit simpler than having to draw a diagram than the last one, and we've got 20 electrons. So if we want to know the number of atoms of calcium in that number of electrons, all we do is take the number of moles and times it by Avogadro's constant, and we get 7.525 times 10 to the 22. Now that is the number of atoms of calcium. This question asks you for the number of electrons. So we know that per atom of calcium we have 20 electrons. All we do is take that number and we times it by 20, and we get 1.505 times 10 to the 24. But all we have to do is look, and where is that number? It's 20, and therefore I will have 20 electrons per atom, and therefore I can times my number of atoms by 20. So we're going to now look at molar gas volume, and we'll do more videos about this in more detail, but this is merely an introduction to molar gas volume. So what is molar gas volume? So molar gas volume is, first of all, 24. And what it means is, at room temperature and pressure, which is RTP, if you recognise RTP, if you see RTP, okay, that means room temperature and pressure. Room temperature is usually about 20 degrees, room pressure is about 1 atmosphere. But if you see room temperature and pressure, 1 mole of any gas is equal to this 24 I just said. So 24 decimeters cubed. Really important you know the unit. And that means there'll be 24 decimeters cubed of that gas per mole of that gas. So remember it's 1 mole, so it'll be 24 decimeters cubed per mole. Now, decimeter, 1 decimeter is 1,000 centimeters cubed. So if you want to go from decimeter to centimeters cubed, you have to times by 1,000. And if you're timesing by 1,000, here you can say 24 times 1,000 is 24,000. That means 1 mole of any gas at room temperature and pressure will be equal to 24 decimeters cubed or 24,000 centimeters cubed. Now, what's not gone over in textbooks often and can appear in exams is this also leads to the following. If you have the same volume of any gas and then you make that gas have the same temperature and pressure as other gases. So for example, if we had oxygen and nitrogen and we said we're going to have 20 centimeters cubed of the oxygen, 20 centimeters cubed of the nitrogen, and I'm going to set the temperature and pressure of both of those the same, they'll have the same number of moles. So if you know the volumes match, you can then say, and you know the temperature and pressure matches, you know the moles will also match as well. But let's look at this pictorially. Let's just say I set my temperature and pressure. So I've set my temperature and pressure to 400 and 100 kilopascals. Okay, and then I take 3 samples. So I've got neon, and I have oxygen, and I have water. Now these are not to scale, so if you're looking at the number of balls we have, or molecules, elements or molecules we have, okay, they're not to scale. They're just simplified to help you understand. But as you can see, there's the same number of particles in each one, which theoretically means there should be the same number of moles in each one. We've set the same temperature and pressure, so we've got the same number of moles because there is the same number of particles. Same temperature, same pressure, which that means it will have the same volume. So let's just say that volume is 120 centimeters cubed, and therefore all will have also 0.1 moles. Again, it's not to scale, so don't worry about doing the calculation on the numbers.